artificial intelligence, cognitive, kinematic modeling, and analysis of a 5-degree robotic arm. The control of the robotic arm has been a challenge, and the kinematic problem is defined as the transformation from the Cartesian space to joint space. In this project, I aim to model the forward and inverse kinematic of the industrial robotic arm. An analytical solution for the forward and inverse kinematics of the robotic system is presented in this video to analyze the movement of arm from one point in space to another point. The mathematical modeling developed in this specific application of the robotic kinematics is motivated by the complexity of robotic systems, which possesses highly nonlinear characteristics. The kinematics solution presented in this project is based on the robotic manipulator, which consists of two areas of problems: forward and inverse kinematics. The forward kinematics will determine where the robot manipulator hand will be in all joints, are known as inverse kinematics, and it will calculate what each joint variable must be if the desired position and orientation of end effector is determined. Kinematics modeling for the research work is delineated as follows. All rotational joints of the robotic industrial arm are controlled by servo motors. These servo motors are connected to the Neuro-Morphic microcontroller CPU, which is controlled by the main computer system. The sensor is placed in front of the arm so that it can read the distance between the gripper and the reflected surface. The industrial robotic arm integrates an infrared sensor. The system is a modular arm consisting of 5 rotary joints plus the end effector, which is a grip. The 5 rotating joints consists of one joint for base rotation, one joint for shoulder rotation, one joint for elbow rotation, one joint for wrist rotation, and one for grip rotation. Kinematics studies the motion of bodies without consideration of the forces or moments that cause the motion. Robot kinematics refers the analytical study of the motion of a robot manipulator, formulating the suitable kinematics models for a robotic mechanism is very crucial for analyzing the behavior of robotic manipulators specific to artificial intelligence robotic systems. There are 2 different spaces used in kinematics modeling of manipulators. One is the Cartesian space and the other is Quaternion space, which is the transformation between two Cartesian coordinate systems that can be decomposed into a rotation and a translation. Two main solution techniques for the inverse kinematics challenges are analytical and numerical methodologies. In the first type, the analytical, the joint variables are solved analytically based on the given configuration data. There are two approaches in the analytical methodology, that is geometric and algebraic solutions. The geometric approach is applied to the simple robot structures such as 2, 3, 4 DOF planar manipulators. For the manipulators with more links and whose arms extend into 3 dimensions or more, the geometry gets much more difficult. In this case, algebraic approach is more beneficial for the inverse kinematic solution. Quaternion filtering and modeling systems. The Quaternion vector pairs are used as an alternative methodology for driving the robotic kinematics of serial manipulators. The successive displacements in the methodology provides a very compact formulation for the kinematics equations, and also to reduce the number of equations obtained in each goal position according to the matrix counterparts. The Quaternion mathematical equation Q is the sum of a scalar S and 3-dimensional vectors V. It is a quadrinomial expression with real angle theta and an axis of rotation n equals ix plus jy plus kz, where I, j, and k are imaginary numbers. It may be expressed as a quadruple. Q equals open parenthesis theta, comma x, comma y, comma z, close parenthesis, or as a scalar, and a vector q equals to open parenthesis theta u close parenthesis, where u is equal to x, comma y, comma z. Industrial Revolution 4.0. Innovations in artificial intelligence, cognitive neuro-morphic, machine vision, robotics, deep learning, and data analytics are enhancing and improving our quality of life. As intelligent machines learn from their environment and execute self-error correction in order to successfully complete a task and ultimately to optimize productivity. The framework of this project is to illustrate and to present the control and driving mechanisms of robotic arms. And the main theme is to grab different size objects which has applications within the industry and other different working environments. The robotic arm is functional, is light in weight, and it provides different attachments and controls in several interdisciplinary that characterizes mechatronics between the notions of mechanical engineering and also artificial intelligence and cognitive computing systems. The artificial intelligence robotic arm and the infrared sensor system. The arm is a modular arm consisting of five to six rotary joints. In addition, the end effector, which acts as a grip. The rotating joints consist of joint for base rotation, for shoulder rotation, for elbow rotation, for wrist rotation, and also for grip rotation. The 6 servo motors are chosen based on torque for proper operation. The infrared sensor is a sharp and is a distance sensory device composed of an integrated combination of position sensitive detection and infrared emitting diode, and also the signal processing artificial intelligence circuitry system. The device outputs the voltage corresponding to the detection distance, and every rotational joint of the arm is controlled by several servo motors. These motors are connected to the microcontroller, which is essentially a Neuro-Morphic CPU system, which is controlled by the methodology and the system software based on Python and C++. The sensor is placed in front of the arm above the gripper, so it can read the distance between the gripper and reflected surfaces. Methodology for controlling the artificial intelligence robotic arm. The control arm can be evaluated in many levels of logical abstraction. In the framework, in the context of this environment, we are mainly interested in high-level tasks of desired trajectory defined in 3D, three-dimensional task space. There are 3 phases. Phase 1 is the trajectory planning. Phase 2 is the inverse kinematics. And phase 3 is the motor control, which I am illustrating in this video presentation and this project. The trajectory planning enables the robot, in this case, in this specific application of the robotic industrial arm. So it enables the robotic end effector to move from an initial position to another position. This transition forms the basis for many high-level tasks like reaching objects or avoiding obstacles. I have implemented the correct trajectory and also defined the inverse kinematics for the system infrastructure. The remaining task is to issue the correct motor commands to the joints of the industrial artificial intelligence robotic arm. These motor commands produce torques that lead to desired accelerations and therefore to the planned movement of the industrial robotic artificial intelligence arm. So depending on the actual robot, many different actuators can be used to produce joint torques. The complex Python mathematical algorithms must be able to perform the projections, local regressions, and distance metric adaptations in an incremental fashion without storing the data. Therefore, the complex mathematical algorithm keeps a number of variables that hold sufficient statistics for the software algorithm to perform the required calculations incrementally.